Let's see how we can prove the chain rule. The chain rule states that dfg dx is equal to dfg dg times dg dx. This looks like a straightforward result of cancellation. Yet, the proof of the chain rule is not that straightforward. Before we take a look at the correct proof of the chain rule, first of all, let's take a look at the flawed proof of the chain rule. This flawed proof is not totally wrong, but it is not perfect in some sense. And this proof actually appears on some textbooks. The proof goes like this. First of all, we consider dfg dx as this limit, according to the definition of derivatives. And then I divide and multiply gx plus delta x minus gx so that it looks like the result of the chain rule. And then we can evaluate the limits one by one, as we have assumed that all functions are differentiable, and so all these limits should exist. Next, I should do a substitution so that gx is equal to u, and then gx plus delta x minus gx is equal to delta u. And as a result, gx plus delta x can be written as u plus delta u. And as delta x approaches 0, delta u should approach 0 as well. Therefore, now this limit becomes the limit of fu plus delta u minus fu over delta u as delta u approaches 0. As a result, this is exactly dfu du, and this is exactly dgx dx. Therefore, we have obtained the result of the chain rule, which is dfg dg times dg dx. This proof looks perfectly sensible, yet it is not perfect, and the only flaw is here. We cannot guarantee that gx plus delta x minus gx must be non-zero. If the denominator is 0, then the whole thing would make no sense. No matter how close to 0 delta x is, it is still possible that gx plus delta x minus gx would become 0 as delta x approaches 0. One example is this function. In this example, it is possible that this function is equal to 0 even though delta x is not equal to 0. That means in this example, as x approaches 0, we are dividing 0, and it makes the whole thing meaningless. Therefore, the proof of the chain rule is difficult because we need to avoid dividing 0. Now let's take a look at the correct proof of the chain rule. First of all, we let E1 be the difference between delta f over delta u minus df du, and E2 be the difference between delta g over delta x minus dg dx. E1 and E2 can be understood as the error between the actual derivative and the approximate derivative. In this regard, we should know that as delta u approaches 0, this error should approach 0 as well. And as delta x approaches 0, this error should approach 0 as well. After rearranging the terms, we can rewrite fu plus delta u as fu plus f prime u plus E1 times delta u. And then we can rewrite gx plus delta x as gx plus g prime x plus E2 times delta x. It is actually possible that delta u is exactly 0 as delta x approaches 0. But it doesn't matter because even though this formula is meaningless, this formula is still meaningful. And we start with this statement to do the proof. Now dfg dx by definition is equal to this limit. Then by this, we can rewrite gx plus delta x as this. And then we can let this gx be u, and then we can let this whole thing be delta u, so that as delta x approaches 0, delta u would approach 0 as well. And afterwards, we can rewrite this as fu plus delta u minus fu. And then according to this, fu plus delta u can be written as something like this. And then fu can be cancelled, so that we can obtain something like this. Because delta u is just equal to this, therefore after doing the backward substitution, we can obtain this result. And after cancelling delta x, we can obtain this. Now we can evaluate the limits one by one because both limits exist. And because delta x approaching 0 would mean delta u approaching 0, therefore we can rewrite this limit as delta u approaches 0. Afterwards, we can refer to this. As delta u approaches 0, E1 would approach 0. And as delta x approaches 0, E2 would approach 0. Therefore, the result of this limit is simply equal to f prime u times g prime x, which is then exactly the result of the chain rule. This is the proper proof of the chain rule, and it guarantees that when we apply the chain rule, we can decompose the function into any differentiable functions that we want.